Welcome to Ultimate Sleep Doctor. Tonight, we'll journey to the very edges of our solar system. Beyond Neptune, a vast, frozen realm exists, the Kuiper Belt. It's a place of ancient ice, remnants of the solar system's formation, and home to countless dwarf planets like Pluto. This is a region of quiet darkness, a space where time itself seems to slow. Consider the immensity of it all, the stillness of the void. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift. Let's begin. Long, long ago, before the Earth even had oceans, our solar system wasn't quite the tidy place we see today. It was a swirling, chaotic mess of gas and dust, a vast protoplanetary disk left over from the birth of our sun. This disk, a remnant of the giant molecular cloud from which the sun had sprung, was teeming with material, tiny grains of rock, metal, and ice, all orbiting the newborn star. Scientists believe this process of creation began with the gravitational collapse of a massive cloud of interstellar gas and dust. The sun's formation initiated a powerful outward pressure, while gravity relentlessly pulled the remaining material inwards, gradually forming a disk. Within this disk, particles began to collide and stick together through electrostatic forces, a process known as accretion. These collisions weren't always gentle. They were often violent, shattering and reforming the clumps of material. But over immense timescales, this process built up larger and larger bodies, planetesimals, then protoplanets. Now, this initial stage of planet formation wasn't without its troubles. The inner solar system, closer to the sun, was particularly unstable. The heat from the young sun meant that the volatile materials, substances that easily evaporate, like water, methane, and ammonia, were largely pushed inwards. Only the most robust materials, like rock and metal, could survive in this scorching environment. However, this is where Neptune enters the story, a truly pivotal character in the creation of the Kuiper Belt. Scientists have developed a widely accepted model called the NICE model to explain the early evolution of our solar system. This model proposes that Neptune, originally much closer to the sun, underwent a dramatic journey outward. Neptune's migration wasn't a slow, steady drift. Instead, it's thought to have been a chaotic series of gravitational interactions with other giant planets, Jupiter and Saturn primarily, causing it to spiral outwards, eventually settling into its current orbit. This outward migration wasn't just a change in location, it fundamentally reshaped the entire solar system. As Neptune moved, it flung countless planetesimals, small, leftover bodies from the initial planet formation, out into the distant reaches of the solar system. These weren't just flung straight out. Neptune's gravity created complex orbital resonances, forcing these planetesimals into elongated, tilted orbits. These are the orbits that characterize the Kuiper Belt. The Kuiper Belt itself is, therefore, essentially a vast reservoir of these scattered planetesimals. It's a donut-shaped region extending roughly from 30 to 55 astronomical units, AU from the sun, an astronomical unit being the distance between the Earth and the sun. At the edges of this belt, the density of KBOs, Kuiper Belt objects, decreases dramatically. The objects themselves are incredibly diverse. Many are icy, ranging in size from small pebbles to dwarf planets like Pluto. Pluto, for instance, is a large, icy body with a surprisingly complex geology. However, not all KBOs are just frozen water ice. Some contain significant amounts of other volatiles, including methane and ammonia, detected through spectroscopic analysis. Spectroscopic data, gathered by missions like New Horizons, which flew past Pluto and Arrokoth, and the Spitzer Space Telescope, has been invaluable in understanding the composition of these objects. By analyzing the wavelengths of light reflected or emitted by the KBOs, scientists can determine what they are made of. The spectra reveal the presence of various molecules, offering clues about the conditions under which these objects formed. For example, the detection of methane on Pluto suggests it formed in a colder environment than previously thought. Moreover, scientists have identified carbonaceous chondrites, a type of meteoritic material within the Kuiper Belt, suggesting a connection to the building blocks of the inner solar system. The distribution of KBOs isn't uniform either. Some regions are densely packed with objects, while others are relatively empty. This distribution is influenced by the gravitational scattering caused by Neptune and other giant planets. Furthermore, the Kuiper Belt isn't just a random collection of icy bodies. It's sculpted by the sun's light. The light from the sun pushes against the KBOs, creating a slight recession effect, and the gravitational influence of the giant planets continues to shape their orbits. The edge of the belt, therefore, isn't a sharp boundary, but rather a zone of gradual transition. Interestingly, the existence of population IV stars, hypothetical stars formed in the very early universe with extremely low metallicity, the abundance of elements heavier than hydrogen and helium, has sparked debate about the origins of the material that formed the Kuiper Belt. Some theories propose that a significant portion of the KBOs, building blocks, originated from the debris of these early, metal-poor stars, dispersed throughout the galaxy during the early stages of our galaxy's formation. This would have provided a rich source of carbonaceous material, further explaining the diversity observed within the Kuiper Belt. It's a fascinating and complex story, one still being actively investigated by scientists today. The Kuiper Belt is a testament to the chaotic and dynamic processes that shaped our solar system, a beautiful and distant echo of the solar system's tumultuous beginnings. The Kuiper Belt isn't a quiet, orderly place despite appearances. It's a swirling, chaotic dance of icy bodies, each influenced by the gravity of countless others and the giants of our solar system. Understanding its dynamics is like trying to predict the path of a pebble rolling down a complex, ever-changing hillside, incredibly difficult and constantly shifting. The basic story begins with the birth of the belt itself. Following the nice model, Neptune's journey outwards, a significant disruption flung vast numbers of planetesimals, the building blocks of planets, beyond the orbits of the gas giants. These weren't neatly arranged. They were scattered, creating the raw material for the Kuiper Belt. But the initial scattering was just the beginning. The KBOs themselves are constantly interacting. There are several distinct populations, each with vastly different orbital characteristics. Short-period KBOs, those with orbital periods of less than 200 years, are generally found closer to the Sun, influenced heavily by Neptune. Their orbits are often highly inclined, tilted relative to the plane of the solar system, reflecting the chaotic history of their formation. Long-period KBOs, with orbital periods stretching for thousands, even millions of years, come from a much more distant origin, possibly from the scattered objects beyond Neptune's orbit, sometimes referred to as the scattered disk. These are the most eccentric, most tilted, and often most distant members of the belt. Then there are the Trojans, grouped into two camps, the Jupiter Trojans and the Neptune Trojans. Jupiter Trojans share Jupiter's orbit, residing just beyond the orbit of Mars, while Neptune Trojans share Neptune's orbit. These groupings offer a fascinating glimpse into the forces at play, with Jupiter exerting a significant gravitational influence on the entire belt. The key to understanding this complex interaction is chaos theory. This isn't about randomness, but rather sensitivity to initial conditions. Imagine pushing a small child on a swing. A tiny nudge at the right moment can dramatically alter their motion, sending them soaring wildly. Similarly, in the N-body simulations used by astronomers, even the smallest difference in a KBO's initial velocity or position can lead to vastly different trajectories over time. These simulations use Newton's laws of motion to track the gravitational forces between all the bodies, constantly updating their positions and velocities. Sophisticated algorithms account for the fact that gravity weakens with distance and that the bodies aren't perfectly spherical. They have slight bulges that influence the gravitational forces. One particularly interesting system is the Pluto-Charon binary. Pluto's orbit isn't a simple ellipse, it's a figure-8 shape, primarily due to the gravitational tug-of-war between Pluto and Charon, its largest moon. Charon acts as a shepherd, stabilizing Pluto's orbit. Without Charon's influence, Pluto's orbit would quickly spiral out of control. The orbital evolution of this system is a prime example of how gravitational interactions can refine and stabilize chaotic motions. Similar stabilizing effects occur in other binary KBO systems, like the Eris-Dysnomia system. Dysnomia, Eris's moon, helps to keep Eris's orbit relatively stable, preventing it from colliding with other KBOs or being flung out of the belt. These shepherd planets, although small in comparison to the giants, play a crucial role in the belt's overall structure. To paint a more complete picture of the belt's evolution, scientists employ hydrodynamical simulations. These models treat the KBO population as a fluid, a continuous mass of icy particles, allowing them to accurately capture the effects of collisions and accretion. Over billions of years, KBOs have been constantly colliding, merging, and breaking apart, gradually growing larger and forming larger bodies. This process is still ongoing, though at a much slower pace. However, not all KBOs remain within the belt. Gravitational scattering, particularly by the giant planets, can eject KBOs from the solar system entirely. A sufficiently strong gravitational interaction can change a KBO's velocity enough that it escapes the sun's pull. These scattered objects then drift into the distant reaches of the galaxy, potentially becoming short-period comets or influencing the orbits of other stars. The future of the Kuiper Belt is uncertain. While most simulations suggest that the belt will persist for billions of years, the continued gravitational influence of the giant planets and the ongoing process of collisions will inevitably shape its evolution. It's a dynamic, ever-changing realm, a testament to the power of gravity and the enduring forces that shape our solar system. The data from missions like New Horizons continues to refine our understanding of this fascinating and complex region, providing new clues to the enduring secrets of the Kuiper Belt. The story of Pluto is a surprisingly complex one, a tale of discovery, scientific debate, and ultimately, a shifting understanding of what it means to be a planet. It began in 1930 with Clyde Tombaugh, a young astronomer working at the Lowell Observatory in Flagstaff, Arizona. He spent months painstakingly comparing photographs of the sky, searching for the subtle movement of stars, a tiny wobble that would reveal the presence of an unseen world. His persistence paid off. A slight blip, a momentary darkness, indicated the presence of a planet lurking beyond Neptune. This newly discovered world was named Pluto, a fitting name derived from the Roman god of the underworld, a fitting reflection of its distance and mysterious nature. For decades, Pluto was considered the ninth planet of our solar system, a respectable, if distant, member of the celestial family. However, the 20th century brought with it increasingly sophisticated telescopes and a deeper understanding of the universe. In the 1990s, astronomers began to notice some peculiar behaviors among the Kuiper Belt objects, icy bodies residing beyond Neptune. These objects weren't simply drifting through space. They were interacting with each other, their orbits affected by the gravitational pull of Neptune and, to a lesser extent, the other giant planets. The discovery of Eris in 2005, a similarly sized object, intensified the debate. Eris was so large that it challenged the existing definition of a planet, sparking a critical discussion within the scientific community. The International Astronomical Union, IAU, the organization responsible for naming and classifying celestial objects, recognized the need for a clearer definition. In 2006, they established 3 criteria for a celestial body to be classified as a planet. Firstly, it must orbit the Sun. Secondly, it must be massive enough for its own gravity to pull it into a nearly round shape, what scientists call hydrostatic equilibrium. And thirdly, and perhaps most significantly, it must have cleared its neighborhood of other objects. This last criterion proved to be the deciding factor for Pluto. Clearing the neighborhood essentially means that a planet has become gravitationally dominant in its orbital zone, having either swept up or flung away other objects of comparable size. Neptune, Jupiter, and Saturn had long since achieved this, dominating their respective regions of the solar system. Pluto, however, shared its orbital space with a vast population of Kuiper Belt objects. It was part of a crowded, complex system, lacking the gravitational dominance needed to be considered a true planet. Its orbital path intersected with many other KBOs, demonstrating that it hadn't exerted a controlling influence on its surroundings. The New Horizons mission, launched in 2006, provided an unprecedented opportunity to study Pluto up close. After a 7-year journey, the spacecraft arrived at Pluto in July 2015, sending back a stunning array of images and data. The surface revealed a far more diverse and geologically active world than anyone had anticipated. The most striking feature is Sputnik Planitia, a vast, smooth plain stretching over 100 kilometers across, composed primarily of nitrogen ice. Scientists believe this plain is created by the sublimation, the direct transition from solid ice to gas, of nitrogen ice, driven by Pluto's surprisingly cold temperatures. The movement of this nitrogen ice creates convection currents, similar to those found in Earth's atmosphere, leading to the formation of this vast, polygonal plain. Beyond Sputnik Planitia, Pluto's surface is a chaotic mosaic of craters, mountains, and valleys, sculpted by billions of years of impacts and geological processes. The spacecraft detected a surprising abundance of water ice, alongside nitrogen and methane ice. The distribution of these ices isn't uniform. Certain regions are rich in water ice, while others are dominated by nitrogen or methane, suggesting a complex history of resurfacing and volatile transport. Spectroscopic analysis revealed the presence of organic molecules, further hinting at the potential for prebiotic chemistry, the building blocks of life within Pluto's icy depths. Pluto isn't a lonely, frozen world. It's accompanied by a large moon, Charon, which is almost as big as Pluto itself. Charon's surface is characterized by fault scarps and a surprisingly bright, nitrogen-rich polar region. The Pluto-Charon system is locked in a tidal dance, influenced by the gravitational forces of Neptune. Interestingly, Charon exhibits signs of geological activity, including evidence of cryovolcanism, a volcanic activity involving the eruption of volatile substances like water, ammonia, or methane instead of molten rock. Scientists theorize that heat from radioactive decay within Pluto and Charon's interiors drives this activity, pushing up plumes of icy material onto their surfaces. Ongoing research focuses on understanding the history of Pluto's volatile transport and the processes that have shaped its surface. Cryovolcanism remains a key area of investigation, and scientists are searching for evidence of subsurface oceans warmed by radioactive decay. The New Horizons data, combined with continued observations from Earth-based telescopes, is slowly unveiling the secrets of this distant, enigmatic world. The debate surrounding Pluto's classification highlights a fundamental shift in our understanding of planetary formation and definition. It demonstrated that simply size isn't enough. Orbital dominance is a crucial factor. Pluto's story isn't about losing a planet. It's about refining our understanding of the universe and the diverse, fascinating worlds that populate it. The Kuiper Belt, a vast and mysterious region beyond Neptune's orbit, isn't just a scattering of icy bodies. It's a time capsule holding secrets about the very beginnings of our solar system. These distant objects, ranging from colossal dwarf planets like Pluto to countless smaller fragments, have been largely untouched by the processes that reshaped the inner solar system, offering a remarkably preserved glimpse into the conditions that existed when the sun and planets were just starting to form. These KBOs are, in essence, primitive solar system materials. Unlike the rocky planets closer to the sun, which have been subjected to intense heat, pressure, and geological activity over billions of years, the Kuiper Belt has remained frozen, a deep freeze maintained by the incredibly cold temperatures. This cryogenic preservation is absolutely key. The lack of significant sunlight and the vast distances from the sun have allowed volatile compounds, substances that easily transition between solid, liquid, and gaseous states, like water, methane, ammonia, and nitrogen, to remain stable for an astonishing length of time. Imagine a snapshot taken billions of years ago of the solar system as it was shortly after the sun ignited. The conditions were far different, hotter, more turbulent, and brimming with raw materials. Many of these materials, released during the solar system's birth, ended up in the Kuiper Belt, never fully incorporated into planets. These KBOs, therefore, represent a tangible link to that nascent stage. Spectroscopic analysis, the study of light reflected and emitted from these objects, is the primary tool astronomers use to decipher their composition. By examining the patterns of light, we can identify the elements and molecules present on their surfaces. The potential for KBOs to contain organic molecules is particularly exciting. While the cold temperatures might seem inhospitable to life as we know it, the building blocks of life, the simple carbon compounds, can remain stable in these icy environments. Scientists believe that during the solar system's formation, complex organic molecules formed through the action of ultraviolet radiation on simpler compounds could have been delivered to the Kuiper Belt. These molecules, shielded from the harsh conditions closer to the sun, could have continued to evolve and potentially, in some regions, coalesce into structures capable of supporting prebiotic chemistry, the chemical reactions that could lead to the emergence of life. One tantalizing aspect of this research focuses on the presence of amino acids. These molecules, vital components of proteins, are fundamental to all known forms of life. While direct detection of amino acids on KBOs is still a challenge, evidence suggests that some KBOs, particularly those belonging to the carbonaceous chondrite group, are rich in these molecules. Carbonaceous chondrites, which frequently fall to Earth as meteorites, originated from the Kuiper Belt and offer a direct sample of these ancient materials. Analysis of these meteorites has revealed a surprisingly diverse range of amino acids, demonstrating that the potential for complex organic chemistry existed in the early solar system. Furthermore, the discovery of complex organic molecules, including sugars and nucleobases, the building blocks of DNA and RNA, within carbonaceous chondrites has fueled speculation about the possibility of panspermia. The theory that life could have originated elsewhere in the universe and been transported to Earth via these icy debris. Perhaps very early in our solar system's history, seeds of life carried by a KBO were deposited onto Earth, providing a crucial ingredient for life to take hold. This isn't a proven theory, but the possibility remains a compelling one, dependent on the ongoing analysis of KBO samples. The composition of specific KBOs is revealing fascinating details. For example, Pluto, once considered a mere icy ball, has turned out to be incredibly complex. Its surface is a patchwork of nitrogen ice, water ice, methane ice, and other volatile compounds. The discovery of Sputnik Planitia, a vast plain of nitrogen ice, is particularly noteworthy. Scientists believe that this region is actively resurfacing through the sublimation, the transition from solid to gas, of nitrogen ice, driven by the faint sunlight that reaches Pluto. Similarly, other KBOs exhibit unique organic signatures. Some have been detected with surprisingly high concentrations of methane, while others display evidence of complex organic molecules embedded within their icy matrices. The ongoing exploration of these objects promises to unlock even more secrets about the conditions that prevailed during the solar system's infancy. The study of the Eris dysnomia system, a binary KBO system, provides another key area of research. These two bodies, with their complex gravitational interactions, are thought to be relatively pristine remnants of the early Kuiper Belt. Analyzing their composition and surface features can offer insights into the processes that shaped the region as a whole. Ultimately, the exploration of the Kuiper Belt isn't just about understanding the formation of our solar system. It's about gaining a deeper appreciation for the origins of life itself, and potentially the possibility that we are, in a very real sense, made of stardust. The remnants of ancient KBOs scattered across the vastness of space. The vastness of space holds countless secrets, and one of the most intriguing lies nestled far beyond Neptune, the Kuiper Belt. After decades of study, particularly thanks to the incredible journey of the New Horizons spacecraft, we're beginning to piece together a truly remarkable story about this distant region. New Horizons' initial flyby of Pluto was a phenomenal success, revealing a world far more complex and dynamic than anyone anticipated. But that encounter was just the beginning. The mission's continuing observations and the data it's sending back are guiding the way for a new era of exploration, one focused on a systematic understanding of the entire Kuiper Belt. Currently, New Horizons' primary mission goal is to thoroughly characterize the KBOs it observed, particularly those in the Kuiper Belt proper, the region closest to Neptune. It's meticulously mapping the surfaces of these icy bodies, searching for subtle variations in composition and geology. The spacecraft is using its onboard cameras and spectrometers to build a detailed inventory of the belt's population, focusing on identifying brighter targets, those that appear to be rich in volatile ices like nitrogen and methane, which hold clues about the conditions of the early solar system. These brighter KBOs are prime candidates for future, more detailed study. But the New Horizons mission isn't solely about individual KBOs. A key aspect of its ongoing work is identifying targets, specific KBOs that appear to hold the greatest scientific potential. These aren't necessarily the largest or brightest. They are chosen based on a combination of factors, including their orbital characteristics, spectral signatures, and potential for holding unique geological features. These identified targets are then prioritized for potential follow-up missions, essentially establishing a roadmap for a sustained exploration effort. The concept of a dedicated Kuiper Belt survey spacecraft is rapidly gaining traction among planetary scientists. Unlike New Horizons, which was designed for a single, focused flyby, a survey spacecraft would be built specifically to systematically map the entire Kuiper Belt. Imagine a robotic explorer, equipped with powerful telescopes, advanced spectrometers, and a suite of sensors designed to withstand the extreme cold and radiation of this distant region. This spacecraft wouldn't attempt a flyby. Instead, it would orbit the Kuiper Belt, continuously gathering data and creating a high-resolution map of the entire area. This map would allow scientists to identify and characterize thousands of KBOs, revealing a far more complete picture of the belt's structure and composition. Reaching the Kuiper Belt, however, presents significant technological challenges. The sheer distance, over 3 billion miles, demands innovative solutions for propulsion and communication. Current chemical rockets are simply too inefficient for interstellar travel. This is where technologies like ion propulsion are becoming increasingly important. Ion engines use electricity to accelerate ions, producing a very gentle but continuous thrust. While the thrust is small, it's incredibly efficient, consuming far less propellant over long distances. Advanced sensor technologies are also critical. These would need to be able to detect faint signals, analyze spectral data with high precision, and operate reliably in the harsh environment of the Kuiper Belt. Looking further ahead, the possibility of robotic probes designed for interstellar travel is a compelling one. Concepts like Breakthrough Starshot, which proposes using laser beams to propel tiny spacecraft to a fraction of the speed of light, offer a tantalizing vision of reaching the outer solar system within decades. While still largely theoretical, advancements in laser technology and lightweight materials are making these ideas increasingly feasible. These probes wouldn't be designed for immediate return. Instead, they would transmit data back to Earth, providing a constant stream of information about the Kuiper Belt. The prospect of sample return missions, bringing back pieces of a KBO, is another exciting possibility. Collecting a small sample of icy material from one of these distant bodies would provide an unprecedented opportunity for detailed analysis in terrestrial laboratories. Scientists could study the composition of the sample using a wide range of instruments, searching for organic molecules, looking for evidence of past or present geological activity, and potentially even discovering signs of prebiotic chemistry, the building blocks of life. The challenges here are immense. Designing a spacecraft that could collect a sample, safely return it to Earth, and protect the sample from contamination are formidable. Furthermore, the ongoing exploration of the Kuiper Belt is prompting scientists to consider the possibility of a second, icy giant planet beyond Neptune. Subtle anomalies in the orbits of certain KBOs, combined with data from New Horizons and other observations, suggest the potential for a yet undiscovered world. This icy giant, if it exists, would likely be smaller and less massive than Neptune, and it could have a significantly different composition. Searching for this potential planet would require a dedicated observational campaign, utilizing powerful telescopes and advanced data analysis techniques. The data accumulated from studying the Kuiper Belt can also shed light on the formation of our solar system. These icy bodies, largely unchanged since the solar system's early days, represent a snapshot of the materials present at that time. They offer a unique window into the conditions that existed when the planets were forming, providing crucial insights into the processes that shaped our cosmic neighborhood. Ultimately, the exploration of the Kuiper Belt isn't just about discovering new objects. It's about understanding the origins of our own planet and the remarkable story of our solar system's creation. And with each new discovery, we move closer to unlocking the secrets hidden in the cold, dark reaches of space. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. We've journeyed through the icy realms of the Kuiper Belt, a distant whisper of ancient beginnings. Let your thoughts drift, calm and unhurried, like stardust settling into slumber. Good night.